All right, today we're going to crack a code. We're going to look at what seems like total chaos, a complex electrical circuit, and find the simple, elegant rules hiding inside. So let's just dive right in. I mean, you look at a circuit diagram for the first time, and it's just a web of lines, right? Symbols, numbers. It can feel super intimidating. It's almost like trying to read a language you've never seen before. A map with absolutely no legend. You've got wires crossing, all these components hooked up, and it looks like electricity is just flowing in some completely random way. But here's the thing, and this is the secret. It's not chaos at all. It's actually a puzzle, and it has a very, very logical structure. And you know, like any good puzzle, there's got to be a master key, right? A method that lets you unlock the whole thing step by step. So, our first move in solving this whole puzzle is picking the right strategy. See, there are a couple of ways you can track how the electricity is moving, but one of them, well, it's just way, way more efficient than the other. Okay, so this is where we have a crucial choice to make. We could try to track the current in every single wire, but that creates a ton of variables to keep track of. You'd end up with way more equations, way more number crunching. It's a mess. The smarter approach is to use what we call loop currents. Here, we're just looking at the overall current that's circulating in each main loop or mesh. What does that get you? Fewer variables, fewer equations, and a much, much cleaner path to the answer. In this smarter approach, well, that's our master key. It's called mesh analysis. And believe me, it's the foundation for figuring out pretty much any complex circuit you'll ever see. So mesh analysis is really the tool that brings order to all that chaos we talked about. And at its core, it's all built on one fundamental rule, Kirchhoff's voltage law, or KVL for short. All KVL really says is that if you go around in a complete circle, a closed loop, all the voltage you gain from things like batteries has to equal all the voltage you lose across things like resistors. It has to balance out. Mesh analysis is just a really clever, systematic way to apply that one simple rule. And the process is actually pretty straightforward. First, you just spot the basic loops. Those are your meshes. Easy enough. Step 2, you just assign a current to each one. We usually just assume they all flow clockwise just to keep things consistent. And hey, if you guess the direction wrong, no big deal. The math will tell you by spitting out a negative number at the end. And finally, you just walk around each mesh and write down one KVL equation. If you have 2 meshes, you get 2 equations with 2 unknowns. From there, it's just simple algebra. Okay, so we've got the basic rules down, but what happens when the puzzle pieces themselves start getting a little trickier? Yeah, let's level up. All right, now we introduced the dependent source. Think of this as a really special kind of power source. Its output isn't some fixed number. Instead, its value is totally controlled by a voltage or a current somewhere else in the circuit. It's kind of like a component with a mind of its own. You know, it's reacting to what's happening in a completely different part of the puzzle. And these guys come in 4 main flavors. You can have a voltage source that's controlled by another voltage or by a current. And you can have a current source that's controlled by a voltage or another current. This is actually the secret sauce behind things like amplifiers, where a tiny little signal current can control a much, much bigger output. So each one of these creates a really dynamic link between different parts of the circuit. Now, you're probably thinking, okay, this has got to make the math way harder, right? I mean, a new variable that depends on another variable. But you'll be surprised. The solution is actually super straightforward. So here's the trick. Part 1, don't panic. Seriously, you just write your KVL equation and treat that dependent source like it's any other normal independent source. If it's a voltage source, you just pop its value, let's say it's 5 times Ix, right into the equation, just like you would with a plain old 10-volt battery. Okay, and now for the crucial second step. Once you've got your equation written down, you go find that controlling variable, that Vx or that Ix. Then you write a simple little expression for it using the loop currents we already defined. For example, maybe Ix is just the same thing as your loop current I2. Then you just substitute that back into your main equation. And poof, just like that, the tricky part disappears, and you're right back to a standard algebra problem you already know how to solve. All right, so there's one more big complication we might run into. It's a special case, a scenario that kind of seems to break the main rule of mesh analysis. So the problem happens when you have a current source that's sitting right on the border, shared between 2 meshes. Uh-oh. Remember, KVL is all about adding up voltages, but But here's the thing. We have no idea what the voltage is across an ideal current source. So this one component completely blocks us. We can't write a KVL equation for the first mesh, and we can't write one for the second mesh. It really feels like a dead end.
But it's not a dead end. This is where engineers came up with this brilliant little workaround called the supermesh. The whole idea is to just mentally erase that problem component for a second. Just pretend that shared current source isn't there and treat the two meshes as one giant single loop. So how does that even work? Well, it's a two-step move. First, you get one equation from that problem source you ignored. You use a different rule, Kirchhoff's current law, KCL, to write a really simple equation that connects your two loop currents to that source. Something like I2 minus I1 equals 2 amps. Boom, that's equation number one. For your second equation, you just walk around the big outer path of that giant supermesh and write one KVL equation. And there you have it. Two equations, two unknowns, problem solved.
Okay, so now that we've gone through the really tough methods, let's talk about what the experts do. Because once you really get the rules, that's when you get to learn the shortcuts. Seriously, think of these next couple of tools as cheat codes for circuits. For certain very common, very simple layouts, you don't have to go through that whole mesh analysis song and dance. You can use these two really powerful rules to get the answer in literally a single step. Now, these shortcuts only work in specific situations. If your components are in series, connected end to end, like links in a chain, then the voltage gets split up between them. That's the perfect time to use the voltage divider rule. But if they're in parallel, connected across the same 2 points like lanes on a highway, then the current gets split up. And that's where the current divider rule comes in handy. Okay, now this is the part you really have to pay attention to, because it's a little tricky. The voltage divider rule is totally intuitive. The voltage you find across one resistor is proportional to its own resistance. Makes sense, right? Bigger resistor gets a bigger piece of the voltage pie. But the current divider rule is the exact opposite. It's kind of weird. To find the current going down one path, you actually use the resistance of the other path in your calculation. Why? Well, just think of current as being lazy. Most of it is going to take the easy way out, the path with less resistance. And, that's really the whole story here. Circuit analysis isn't just about math. It's about recognizing the structure of the puzzle you're looking at and then picking the right tool for the job. Sometimes you need the powerful, systematic approach of mesh analysis, and other times you can just use the quick, surgical precision of a shortcut. Kind of makes you think, doesn't it? So many things that look like pure chaos on the surface actually have a simple underlying logic. From the way electricity flows to the lines of code that run our favorite apps, the secret is usually just knowing the fundamental rules and knowing how to apply them. So I'll leave you with this. What other complex systems out there are just waiting to be cracked with a simple key?